this mini lecture, I'm going to talk about permutation groups. And I think the hardest thing about introducing ourselves to permutation groups is just understanding the language that's at play. So I'm going to be clear about the language that we mean. So we start with this group Sn, which is called the symmetric group on n elements. And it consists of bijections of a set of n elements to itself. Where the operation is then composition. And we call these elements of Sn, are called permutations. And we use two different methods for denoting elements of Sn. The first is called stack notation. And in stack notation, we put the element on the top. We list all of the elements of Sn on the top. So this would be an element of S5. And then we list where each element maps. So maybe 1 maps to 2, and 2 maps to 5, and 3 maps to 4, and 4 maps to 2, and 5 maps to 1, or something like this. The other notation that we use, which is the notation that I'm going to encourage you to use more, is called cycle notation. And what cycle notation means is that we use parentheses to denote how elements are mapped. So I'm going to start with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 means 1 maps to 2, 2 maps to 3, 3 maps to 4, 4 maps to 5, and then closing this parenthesis here means that I cycle back to the beginning, so 5 maps to 1. So I secretly have arrows here. Or if I had something like 1, 2, 3, 4, 5, what this would mean would be that 1 would map to 2, 2 would map to 3, and 3 would map back to 1. And here, I would have 4 mapping to 5 and 5 mapping back to 4. And I can tell that because of where the parentheses close and then open back up again. By the way, in these cases, I've written these as disjoint cycle, or in this case, I've written these as disjoint cycles, meaning I had no repeated numbers between the first cycle and the second, but there was no reason that I couldn't have written, say, 1, 2, 2, 3. It's not the same element as this one, because there's no 4s and 5s involved. However, there was no reason why I had to write my cycles as disjoint cycles. These are all elements of S5. And so I prefer cycle notation, and I think all of our instructors prefer cycle notation. Moreover, because we're going to be working remotely, it's much easier to write a parenthesis with numbers than it is to write one of these stacks. So I'm going to encourage you to use cycle notation. It's a little less intuitive when you're first learning these, but once you learn to translate between stack notation and cycle notation, it's much easier to work with cycles. In the discussion section on Canvas, we'll explore some of the advantages of cycle notation. And if you're looking for help in translating between stack notation and cycle notation, Part A on your adventure sheet, on the permutations adventure sheet, explores this. And Eric, Ava, and I have made a video where we go through the solution to Part A. So if you're having some trouble there, those are some resources, but I also encourage you to use Canvas discussion and Piazza and office hours to get more help with this in a more robust sort of way. Okay, so I just wanted to introduce this as the language of the symmetric group. And so why are we talking about the symmetric group? Well, I would say there's two reasons why we're doing this. One is because we're building a library of groups that we study. So I'd like to summarize some of the groups that we've seen thus far. Always the place to start is with the integers. And the integers are not a group if we use multiplication, which might be our favorite my favorite operation, but the integers are a group if I use addition as the operation. Likewise, if I take z mod n and use addition, I also have a group. In fact, if I take any ring that we already know and understand well, and use the operation of addition, that will be a group. We proved that last week. It's also the case that if we take the real numbers minus 0, this is a group under multiplication. We have to get rid of 0 because 0 does not have a multiplicative inverse, but everything else does within the real numbers. Also, if we take zp minus 0, where p is prime, this will be a group under multiplication. And if I take the general linear group, or GL2R, so this consists of 2 by 2 invertible matrices with real entries, or entries in R, with multiplication. This is a group. So these are some of our favorite rings, and essentially we're looking at either the additive structure or the units in those rings to allow us multiplicative structure. But not all groups come from rings in this way, and we've seen as one example of this Dn, the dihedral group, which consists of dihedral group, which is the symmetries of the regular n-gon, or irregular n-gon. This was on homework 6 or 7, one of the two. But now we're also including Sn, and these are the bijections or these are bijections of a set of n elements. But again, we sometimes say that this is a permutation, or these are permutations of n elements. And the real advantage to these two groups, Dn and Sn, that do not come from a ring structure, also have this nice property that they are families of groups. And what I mean by families of groups is that there is one group for every natural number, maybe every natural number bigger than 2. D1 doesn't necessarily make sense. S1 is just the identity. These are maybe boring. But once n is 3 here, and I guess 2 here, we start to get groups that are a little bit more interesting. And there's a group for every n. So we get a family of groups, meaning I can just tell you what Dn means, and I have infinitely many of them. So talking about Sn allows me to expand this list. And there's also a particularly interesting subgroup of Sn, which we explore in part D on our adventure sheet. This is a subgroup of Sn consisting of even permutations. And a permutation is said to be even if it can be written as a product of an even number of transpositions. A transposition is a transposition is a permutation that switches two objects in the set. And so transpositions are special types of permutations. And a permutation is said to be even if it can be written as a product of an even number of transpositions. So we explore in our adventure sheet some of ensuring that this is a well-defined definition. But this subgroup, AN, also gives us a family of subgroups. There is one AN that is a subgroup of each SN. So we have a family of these are called alternating groups. Okay, so this is the first reason why studying permutation groups is of interest. It helps us expand our list of groups. Particularly, it helps expand our list of groups by infinitely many groups, and by infinitely many groups that we did not obtain just by taking a ring and forgetting some of its structure. But the other reason that symmetric groups are interesting, and this is a little bit of foreshadowing, this is reason number 2 why symmetric groups are interesting. So this is foreshadowing to the adventure sheet on group actions. This is Cayley's theorem. Which says every finite group is isomorphic to a subgroup of Sn where is isomorphic to a subgroup of Sn for some n. And maybe a hint is n equals to the order of the group will always work. So we will prove this on the adventure sheet on group actions. We need to build up a little bit more information before we get there, but this is one of the reasons, in fact, I would say that this is the major reason why symmetric groups are of interest, or permutation groups are of interest, is because every finite group is a isomorphic to a subgroup of some Sn. Great, thanks.